So what were we discussing in the last class? Yes? Transformer, encoder, right? So how did we start learning transformers? How does the transformer architecture looks like? Yes? Transformer consists of two important blocks. What are they? Encoder and decoder. So we have seen encoder part in the last session. So today we'll complete decoder and then try to build the entire transformer model. Okay. Now when we have seen encoder, what did we cover? So we have seen all those points on the left hand side, right? So we have started with taking a input sentence, tokenizing that input sentence, giving the n-dimensional vector space for each word in the input sentence, and then also finding the position encodings, concatenating what? Word embeddings or the input embeddings with position embeddings, position encodings. Now this would be the input for what? The encoder block. Right? Yes or no? This was step 1. Now what did we see inside the encoder block? So we have two important operations that are being carried out inside the encoder block. One is what? Multi-head attention. The second one is what? Feed forward network. In between these multi-head and feed forward, again we have two blocks. What are they? So after multi-head attention, I add and normalize. Again after feed forward, I add and normalize. Normalize is normalizing the features. But what is this add block? Adding the original input from the given input with what? The updated multi-head attention input. Similarly, I am adding the input from multi-head along with what? The output of the feed forward. So I am using two add and norm blocks here. Okay. So giving this connection of add and norm from the input to the output of multi-head or from the input to the output of feed forward is called as residuals. Okay. So we have seen what is tokenization, input embeddings, position embeddings, residuals, query, key, value, add and norm, and encoder. Okay. So today in the class we will discuss about the decoder block. I'll explain you what are the three important subsets or sub-blocks that we have inside decoder, and then we'll combine the entire transformer architecture by programming the transformer model including encoder block that we have designed yesterday, and then the decoder block that we are going to do today. Okay, so we have two tasks: design decoder first and then design the transformer model using what? The encoder and decoder. Okay. Now, so what we have covered so far? The encoder part. So what are we going to do today? The decoder part. Okay. So before we actually step into decoder, I'll quickly recap what did we see in encoder. Right. So what does encoder do? Encoder is the first important block of what? The transformer model. Okay. So encoder is responsible for what? It takes the input, processes that particular input and generates what? Contextualized or rich context embeddings. What do you mean by contextualized rich embeddings? Which means that with this attention mechanism, I am not just giving the words, I am not just processing the input tokens, but understanding the semantics or meanings associated with each and every word. This is attention mechanism. When I talk about self-attention, what does it come? Comparing one word with its same word and other word such that the importance of that word would be depicted. Okay. So, what do you observe there? The encoder is the first part of the transformer model and it is responsible for what? Processing the input tokens and generating what? And generating context aware representation that the decoder will use. Now, decoder will understand the words, that is the input words, and understands the context of each and every word. Based on that, the decoder will start doing its job. When I say decoder starts doing its job, if I perform translation operation, it starts converting one word to other language. Okay. If I talk about next word prediction, when I give an input sentence, decoder will try to predict the next word based on the given input sentence. So depending on the application that we are working on, the decoder will do its own job. Okay. So what is the example that we are actually discussing in the class? Language translation. So when I talk about language translation, when I give one input in one language, the decoder will start taking the features that are given to the encoder and start generating the translated output of each and every token. Okay. Now, decoder has two sublayers. What are they? Sorry, encoder has two sublayers. What are they? Multi-head attention and feed-forward neural network. Each of these layers are followed by what? Add and layer normalization block. Okay. So, the encoder does not have a look-ahead mask because it processes all the tokens. So, when we were talking about attention mechanism, this is very important point for decoder. Okay. Now, when we were talking about attention block, we first take QKV and then perform matrix multiplication of Q and K transpose, and then we say we are omitting what? That masking operation. I am omitting masking operation because I am processing all the inputs at a time in my encoder, but this will not happen in decoder. Decoder will take, see, when you observe the architecture, when we was talking about concatenation of 6 encoder blocks and 6 decoder blocks, I told you one point. One encoder layer is stacked upon another encoder layer. The final output would be what? The output of the last encoder. But when I give the connections to the decoder, the output of the final encoder is given to what? All the decoders. That is, one output would be generated at a time. Not all the outputs would be generated. Only one output would be generated at a time in the decoder block. Okay. I generate first. Suppose if I say I am ASHA. Okay. I am processing I am ASHA parallelly. Inside what? The encoder block. Hence I say masking is not required because I am processing all the sentences at a time. So that is the reason we say only multi-head attention. But when I talk about the decoder block, when the decoder block receives the word, it starts converting what? The translation of one word, not altogether. One word at a time. That is, first I would be converted, am would be converted, and ASHA would be converted. Are you getting my point? So when in this case, first when I is processed, do I know the next words? I don't know what are the next words. So I have to mask those two words. Hence we use masked multi-head attention inside the decoder block. Okay, I'll explain that later once again. But just understand, we are skipping which step here? Masking steps inside what? Encoder. So that is called as self-attention. That is called as what? Self-attention. Okay. Now that is the point. The encoder does not have a look ahead mask because why are we not using that masking operation inside the attention block? Because we are processing all the tokens parallelly. Please make note of this point. Okay. Now what is the input to the encoder block now? Let's say it has X. What is this X? EP1. What is that EP1? Embedding and positions concatenated together. Okay. Now look at that. The encoder takes a source sequence X as input. See, when I say source sequence, the input sentence, that is my English word. When I say target sequence, that is the translated output that I am expecting. Okay. Please make note of this point. Okay. Now that is the input. For example, in our case, that is a sentence in English and converts it into what? The meaningful representation. Okay. Now in step 1, what are we doing? Input embedding plus position encoding. Okay. Now what do we do in multi-head attention? What do we do in multi-head attention? What is the purpose of multi-head attention? Can you please read that? It allows the encoder to attend all the words in the input sequence, capturing what? Long range dependence. I am processing all the input tokens parallelly. And this is given to what? Multi-head attention block. Inside multi-head attention, what do we have? We have single head attention concatenated multiple times. Okay. Now, how does that work? First, the input X is passed to which block? The self-attention block. Okay. Each token attends all other tokens in the sequence. This is self-attention. Each token will attend what? All other tokens in the sequence, which is self-attention. Okay. Now, when I have attention, that is, attention is all about what? Q, KV, value generation of each word. And then I perform self-attention, which is what? Attending all other tokens within the given sentence. Now, after I am done with attention and self-attention of one block, I concatenate what? N such blocks, which gives you what? Multi-head attention. Okay. Now, what is the output of MHA? The output of MHA is what? The refined representation of the input sequence, where each token has what? context, where each token has what? Context. That is, when I was talking about bat example, okay, which bat is actually describing in that particular given sentence is described after your multi-head attention block. So in simple, just understand that MHA is responsible for understanding the context of the words compared to all other words. Context and the importance of every word in the given input sentence. Okay. So this is all about the first block, which is what? Multi-head attention. What is the second block that we have discussed? Feed forward network. So why are we using this feed forward network? To introduce what? To introduce non-linearity and transform what? The attention output that we get before passing it to the next encoder blocks. What do you mean by next encoder blocks? When I talk about the encoder block, it is not just one encoder. As I told you, it is stack of encoders. So one encoder, after that another encoder, after that another encoder. So the final output would be what? The final output would be the output of the last encoder. So when I was talking about the classic transformer architecture, we have 6 encoder blocks. So each and every multi-head attention thing, whatever we are processing, that will be processed 6 times for the 6 encoder blocks. Okay. Now the self-attention output is passed through what? As we have taken 2 fully connected layers. One fully connected layer, and then I apply ReLU, and then I take another fully connected layer. This is what we have already seen. Okay. Now what would be the output of FFN? The transformed features. Output of MHA is what? The context generated features. What would be the output of the FFN? Transformed features. That is applying software, ReLU, processing through all the encoders, and I get the transformed output after what? Multiple encoder block concatenations. Okay. So this is all about what? The second block, which is feed forward neural network. After that, we have seen 2 additional components. What are they? The residual connections. So what are residual connections? Each sublayer, that is self-attention and FFN, will have these residual connections. And what do? They help us in what? They help us in better gradient flow, such that vanishing gradient problem will be eliminated, and long range, because I am processing all the inputs sequentially, parallelly. So I want to avoid the problem of what? Long range dependencies, and this residual will help us doing that, because I am passing one word, adding that with the second word, and simultaneously giving that to the next sequence. Okay, auto-regressive nature that is available here. Okay. Next, why do we use layer normalization? For normalizing the features with which I'll get my stabilized training. Okay. So what is the final output of the encoder? Transformed matrix or transformed features in a matrix representation. So as you can see, the encoder block is stacked n times. So when I talk about the original classic transformer, what is the size of n? 6. Okay. The final encoded output. What do you mean by final encoded output? The output of the last encoder layer, which I am representing it as what? Z. So what is the input to the encoder? X. What is the output of the encoder? Z, which is from the last encoder. What do you mean by last encoder? The 6th stacked last encoder block. Okay. So now this output is then passed to what? Decoder for further processing. So today we'll see that transformed output from the encoder is how is that taken and how decoder works. Okay. So this is what we have seen till the last class. So when I want to summary, we have MHA block, we have FFN. MHA allows each token to attend all tokens in the output and understand the context. FFN will introduce non-linearity and transform the output of the context vectors. Okay. Now this was the block that we are talking about. Now look at the right side figure. Okay. Observe the figure very carefully and understand what I am talking. Look at the diagram very carefully and observe the arrow marks that I am going to discuss about. Okay. Now, when I talk about the encoder, I said we have 2 blocks. What are they? Multi-head attention, feed forward. Now, when you look into the decoder block, I have 3 sublayers. In the decoder, I have what? 3 sublayers. At the bottom, what do you see? Masked multi-head attention. Above that, what do you see? Add and norm. After that, what do you see? Multi-head attention. Again, add and knock. After that, we have feed forward network. So what is the new thing that you're observing here? Masked multi-head attention. Are you clear with this? What are the three sublayers inside decoder? Masked multi-head attention, feed forward. Okay. Now let's look in depth now. Okay. Now when you see masked multi-head attention, when you look into masked multi-head attention, okay, look at the bottom there. What are the inputs to the masked multi-head attention? Am I giving the input to the masked multi-head attention from the encoder block? No. I am generating new query key values and giving them to what? Masked multi-head attention. Now before that, before I generate QKV, in encoder what did we do? We take X into W of Q, X into W of K, X into W of V, with which we generate QKV values. Similarly, what is that X that I am talking about here in the encoder block? The English sentence, that is source sequence. Please understand this point very carefully. So when I talk about the encoder, please understand this. When I talk about X is the input sequence, which is the source, that is English language, for which I generate what? Attention weights, that is WK, WQ, WV, and I multiply X into WQ, X into WK, X into WV, with which I generate QKV. Now, similarly, in the decoder part, I know my target out sequence also, right? For example, if I take my translation as I love AI, that we were talking about in the coding part. So, what is I love AI translation in Telugu or Hindi or whatever languages you choose, okay? What is that? Telugu aithe? Naku AI ante ishtam, whatever it is, okay? Now, this Naku AI ante ishtam is taken as the input for the decoder block here for training. For what? Training. So, what is the input to the encoder block? Source sequence, which is the English sentence. What is the input to the decoder block here at the bottom? Target sequence. Now again we repeat the same process. What is the same process? Multi-head attention block. What is that multi-attention block? This source target that I have, let's say it as Y. Let's say it as what? Y or X1. X is what? Source, which is given to encoder. X1 is what? The target input, which is the output, which is given as input to the decoder block. Okay. Again I repeat the same process. What same process? Generate Q, KV, X1 into weights of Q, X1 into weights of K, X1, X into weights of, okay. Now here I am performing masked multi-head attention, not normal attention. What is that? I'll tell you. Just understand what is happening inside the decoder block. Did you all understand what is that output shifted right thing? That output is what? The target sequence. Okay. So that target sequence along with what? QKV values generated would be given to masked multi-head attention, with which I generate a output. Now that output is again residual connection added and normalized. Again I generate the output. Okay. Now look at the diagram very carefully now. What is the second block? Multi-head attention. Now look at the arrow marks. Okay. Two arrow marks are coming from where? The encoder blocks. That is the output of the encoder block, which are features. The third arrow mark is coming from where? Masked multi-head attention. It is. Now listen to this point very carefully, which is the heart and soul of the architecture. That arrow mark that is coming from masked multi-head attention is the query. Is what? The query. And converted original output. Key and value are taken from encoder block, that is features. Are you getting? So for this query, I compare this with what? The key and value in the English, and I generate the output. Is it clear? So in the decoder block, for the multi-head attention block, Q is taken from where? Q is taken from the masked multi-head attention, which will actually have what? The translated words. K we are taken from where? K we are taken from the output of the encoder, which will have keys and values. Now this query, when I search, would be compared with the keys and values of the English language. Hence your multi-head attention will start understanding what? The query answer from these keys and values, and try generating your outputs one by one, which will be again processed to what? Feed forward network, and then we'll take the final output. Yes or no? So how is the training happening? How is the training happening here? First we give the input source sequence to the encoder block and process that, where we generate K and V. Where we generate what? K and V. When I talk about the decoder, for the decoder input, what am I taking? The target sequence as input and generating what? The queries. Now, I take another MHA block in the decoder, which will perform operations using what? The queries generated from the masked multi-head attention, which is from the target sequence, compared with what? The K and V values from the source, and hence it generates the translated output. Now this translated output is given to the layer and normalization feed forward, hence one by one the tokens, output tokens would be generated in the decoder block. Now how many times are we doing this decoder operation again? 6 times when you talk about the classic decoder block. Okay. So ఒక్క పాయింట్ అర్థం చేసుకోవాల్సింది ఏంటి ఇక్కడ? For the decoder we have two things: masked multi-head attention, multi-head attention. Masked multi-head attention is similar to this operation, but what are we doing here? Taking the target sequence and performing the same operation of query key values and then generating the output. So the output of masked multi-head is taken as what? Q, which is given as input to MHA in the decoder block, whereas KV are taken from where? The encoder block. This is next I'll explain it in detail. Did you understand that? Please observe the diagram. I'll give you 1 minute. Please observe the diagram. Okay. KV from where? Output of the encoder. Q from where? Output of the masked multi-head attention. Okay. After that, feed forward and then add normalizing, with which I'll be done with decoder. Now what would be the decoder output? Decoder output would be tokens. But I want my language. So that is the reason I again apply to what? I introduced non-linearity. Now I'll apply linear layer, give it to softmax, and then try to unembed the token such that I'll generate my word tokens as my output. Okay. So listen. Input, sentence, encoder, transformed features, target sequence, decoder, the final output, apply to linear layer, softmax layer, and then finally I'll get my tokens, output tokens. Okay. Now look at that. When I talk about scale dot product attention inside encoder block, I am masking that. What am I masking? After scaling, I am masking because I am processing what? All tokens at a time. But when I talk about decoder, in the output, I am taking what? One sequence at a time. Hence, I have to do what? Masking. Andukane that block is called what? Masked multi-head attention. That I will show you in depth again. Okay, so we have already seen this. Same operations. What are those operations? Step 1, X into WQ, WK, WV, where we'll generate QKV. This is step 1. Step 2, Q into K transpose. Step 3, Q into K transpose divided by square root of DK. Step 4, softmax of that. Step 5, multiplying them with value. Same thing will happen in the encoder block. Same thing will happen in the decoder block as well. Okay. Now what is this multi-heads? Concatenating the heads n number of times. Is it clear, everybody? Now, how many heads do we actually have to take is the question here. Okay. So as told in the last class, D model or D dimension is what? D dimension is what? The number of vector space that I am taking for each word. Okay. And then I also take number of heads. Number of heads. So this divided by this will give you how many times I want to process my given input. Okay. This is what we have seen. Now let's get back to the example. Okay. So we have seen what was the sentence that I want to translate. I ate an apple. So first we do tokenization. After that we go for the embedding layer. We generate the embeddings, which is D model, the number of dimension vector that I take for each word. After that we have gone for what? Positional encoding. We have concatenated input embeddings with the positional encodings. And then we have generated what? The final output, which would be given as input to the encoder block. Here in the encoder block, the actual context comes into picture with which mechanism? With attention and self-attention mechanism. Okay. So we perform attention mechanism with this formula, softmax of q k transpose divided by square root of dk into v. Okay. So we generate query q into k transpose, softmax of that into v. Okay. Now look at this. Okay. So yesterday somebody was asking me why only one Q connection was given. Somebody here, right? Yeah, please now understand this. Okay. Now when you observe this diagram, what do you understand here? Look at those Q KVs. Okay. First I take my Q. Okay. Compare that Q with what? Keys. Compare that Q with what? Keys. That's the reason I multiply what? Q into K transpose. Hence I am connecting all the Q's. Query is what? See, for example, if I search for one video on YouTube, I say, let me search for my video that I have recorded yesterday. Okay, this is the query. So when I search ASHA transformers, so I get 3-4 videos. ASHA transformer 1, ASHA transformer encoder, ASHA transformer decoder. So these are keys. What is my search? ASHA transformer. So this I am comparing with what? All the keys. So what is the final value? I'll pick up one value which I actually wanted from the keys generated. So this is how the search engine happens. The same thing is applicable here. This is a final diagram of multi-head attention. Okay. Now, what is that in red box? QK transpose. After that, what do we have? Softmax of that particular thing. That square root of dk I have just eliminated. On the top I have written. Dimension is removed for brevity. For understanding clearly, I have just removed that square root of dk, but that is added. Okay, after that, I give it to what? After softmax, I give it to what? Multiply that with value v. Can you see that v? V is again multiplied. Yes or no? So what is that in red one? Q into K transpose. That is given to what? Softmax. Now that softmax output is multiplied with what? V value. Can you see that arrow marks from V going there to that alpha block? Okay. Now all of them concatenated. Do you find that summation? So that is multi-head attention. So one attention, one attention, one attention, one attention. All of them are concatenated together, which will give you what? One multi-head attention. So similarly we have multiple times for encoder layers. Okay. Did you understand this? Okay. So this is how we get parallelization in the encoder block. All this we have seen already. Okay. Now let's look into the most important block in the decoder, which is what? Masked multi-head attention. Okay. Now look at this. So what is the input sentence that I have taken here? What is the source sentence? I like plants. So I want to convert into some X language. So let's say German here. German language. Okay. So it says Ich mag Pflanzen or whatever it is. Ich mag what? Pflanzen, which is I like plants translation. So what is the input to the encoder block? Target sequence, which is I love plants. What is the input to the decoder block from the bottom to the masked multi-head attention? Translate. So am I processing them parallelly? No. I want to process one word at a time. So first is what? First I want to process my first word. So I don't want second and third to come into picture. So what do? I mask them. Can you see that near masked multi-head attention? To prevent cheating. Cheating is what? When I give second and third, obviously I'll get my output. Here I want to predict the output by what? Masking the next words and just take what? One word. Hence I go for what? masked multi-head attention. If you don't do masking, what will happen? It's like giving the question, giving the answer and ask you to write the exam. Yes or no? I will teach, I will give you the question and I want the answer to be written. I don't want to give question, answer and ask you to write the exam. Are you getting my point? So that is why we use what? Masked multi-head attention. Okay. Now I'll explain you how do we use masked multi-head attention. But before going to that, let's observe the bottom part of the what? Encoder. So what do you observe in the bottom part of the encoder? The target sequence is taken. Okay. Each have n whatever it is. Okay. That target sequence will be taken. They will be converted to tokens. Again same positional encoding. Again concatenating what? Word embedding with positional encodings and generating what? The final X. That is EP1 here again. What is it EP1? The embedding and position of the target sequence that I have taken. Okay. Now look at this. Masked multi-head attention. Okay. First, look at that. First, I want to process SOS. What is SOS? Start of sentence or start of sequence. Okay. Then I want to process what? The first word only. Where I want to mask what? All the words. In the second step, what do I do? SOS, first word and then second word. So that upper triangle thing, I want to mask it. Are you all with me? Yes or no? Okay. So, is this parallelizing? No, I am not doing parallelizing, but I am doing what? Masking. Hence, in encoder we have multi-head attention. In decoder we have what? Masked multi-head attention. Okay. Now, but again there is a problem. I want to mask it, but simultaneously I want to do the operations. That is parallel operations, because I don't want to go sequence by sequence and waste time. Because when you talk about I ate an apple, I love AI, 3-4 words. In general, you may have some millions and billions of words that you give as input to the transformer block. So I want to do masking. At the same time, I want to process them parallelly. So what do I do is, I mask them. Masking them is what? Hiding those values, converting them into applying some activation function to that, and then converting them to 0 or some values. Okay. I am performing masking. But what am I doing? I am nullifying those particular masked values such that I can do what? Parallelization. Are you all clear? Yes or no? So this is what happens inside which block? Decoder masked multi-head attention block. Okay. After that I again go for what? Adding and normalizing. In this normalizing I do that. Can you see? Observe the figures very carefully. Observe that normalizing block. Can you see something inside that normalizing block? What do you see? Nullified values. So here I am normalizing them in this step of add and normalizing after what? Masked multi-head attention block. Okay. Now, what is decoder self-attention doing? Decoder self-attention is what? Queries from the encoder inputs, keys from the encoder inputs, values from the encoder inputs. But when you talk about decoder mask self-attention, queries from the decoder inputs, keys from the decoder inputs, values from the decoder inputs. Okay. This is for MHA, not masked multi-head. This is for what? MHA, the next step that I was talking about. Okay. After MHA, do I what? I go for feed forward and concatenate that what? 6 number of times for 6 decoder layers inside the classic transformer. Okay. After that, I give it to what? The linear layer, and then what? The softmax for predicting the output possibilities. Okay. So this is how we design what? Decoder block of the transformer. Okay. So we are talking about this example, right? Yes or no? Taking the input sequence, finding the vocabulary size. After that, generating embeddings. After that, generating what? Positions. Concatenating position embeddings with what? Word embeddings. The resultant matrix is given as input to the encoder. What will happen inside encoder? Masked multi-hit attention will happen inside the encoder where the input would be multiplied with what? The query key values with which I generate what? QKV values. After that I perform Q into K transpose divided by square root of dk, applying softmax to that, multiplying that with V. So this is the final output of MHA. After MHA, what do I do? After MHA, I add and normalize. Adding with what? MHA output added with what? Output of input encoding and positional encoding. And then normalizing the values. After that, giving it to what? Feed forward, where what will happen? One fully connected layer, ReLU, another fully connected layer. Okay, fully connected layer is what? X into W plus B. Apply ReLU to that and give it to another fully connected layer, add and normalize that. So this is what we have seen in the encoder. Now let's see the decoder part. Okay. So what do we do in decoder? Same again, embedding generation for what? The output target sequence. Okay. All the calculations are same like what? Same like encoder. Let's understand masked multi-head. So what are we doing? The linear projections in the masked multi-head are done by masking the next values by just considering the present state. And then we are calculating what? The next word using what? The MHA block and then feed forward block. Okay. So after that we finally get what? The resultant matrix is 6 by 6, but I want the words tokens to be generated, for which we go for what? Flattening in the linear layer, and then we go for softmax for predicting the probabilities. Okay. So what is the transformer decoder block doing here? What is the transformer decoder block doing? The decoder block is a crucial part of the transformer which is primarily used in sequence to sequence task. What do you mean by sequence to sequence task? Language translation, text summarization, or chatbot, question answer generations, or so on. Okay. So how many blocks are there in the decoder? 3. What are they? Masked multi-head attention, masked multi-head self-attention, multi-head cross-attention. Now understand this. Yes. Listen. When I talk about MHA, listen to me. When I talk about MHA, query key values are from the decoder. So this is called self-attention. When you take encoder also, for MHA, query key values are generated together. So MHA of encoder, masked MHA of the decoder will use what? Self-attention, because QKV are individual. But when I talk about MHA of decoder, that attention is called cross-attention. Why? Queries are from masked MHA, keys and values are from. Are you getting my point? So this will be given in your exam, multiple objectives. What is cross-attention and what is self-attention? Which blocks employ self-attention? Encoder MHA, decoder masked MHA. Which block employs cross-attention? Decoder MHA. Why? Because for the decoder MHA, queries are from masked MHA, whereas key values are from. Okay, so can you see that point? So I am talking about what? The decoder has 3 important blocks. What is the first block? Masked multi-head self-attention. What is the second block? Multi-head cross-attention. Third block is what? Feed forward neural network. Are you all clear with this? Okay. Now what is the input to the decoder? Input to the decoder is not the features. Input to the decoder is what? The target sequence, which I am generally calling it as what? Y. What is output of the decoder? Z, the transform output. Okay. Sorry. What is the encoder output? Z. You have taken, right? X is encoder input. Z is encoder output. What is decoder input? Y. What is decoder input? Y. Understand this carefully. X is what? Input to the encoder. Z is what? Output of the encoder. What is Y? Input to the decoder. Got it? So what does decoder block take? The target sequence which is in Y. What is the output for the encoder? Which is what? Z. Okay. The decoder process, listen to that point very carefully. The decoder process what? The target sequence in an autoregressive manner. What do you mean by autoregressive manner? One word and then other word combined together, third word, two words combined together and so on. Okay. Meaning it only looks at past tokens while generating the next one. Okay. Now what is masked multi-head attention doing? What is masked multi-head attention doing? Allows the decoder to attend to the previous words in the target sequence. Ensure that the decoder cannot peek ahead. What do you mean by peek ahead? Does not cheat by looking at the next word for predictions. Okay. So the input target sequence Y is embedded and positionally encoded. Yes or no? Okay. That sequence is passed to which block? Self-attention inside masked multi-head, and then we generate the look ahead mask here. So here in this attention we use that masking. In encoder we were not using masking, but here inside masked multi-head attention block we will use that masking. In the code you will clearly understand that. Okay. What does second block do? Second block is what? Multi-head cross attention. Now please listen to this carefully. Helps the decoder attend to relevant parts of the encoder output. This is where, now listen to this. This is where the decoder learns dependencies between what? Source and target. Source is from where? Encoder. Target is from where? Decoder. So when I talk about source key values. When I talk about target query. Okay. Now look at that. The queries come from where? The queries come from the decoder's self-attention output, whereas the keys and values come from encoder output, which is Y. Are you all clear? Next is multi-head attention applied. So the output of this block would be what? The information from both source and target sequences. Now this is again given to what? Feed forward, which applies non-linearity and transforms the attention output before passing it to the next encoder layer. Okay. So the cross attention is passed through two fully connected layers. Same two fully connected layers. One fully connected layer, ReLU, another fully connected layer, and the output of this block is given to the next of the decoder layer. What do you mean by next of the decoder layer? Stacked decoder layers. In this way I get my translation done. So what are the additional components again here? After each sublayer I have what? A skip connection, that is a residual connection, which helps in what? Better gradient flow, avoiding vanishing gradient. Layer normalization I am applying after each sublayer such that it will stabilize my training. Okay. So what would be the final output of the decoder block? The final output of the decoder block would be what? The decoder stacked n times. So what is that n here? N is equal to 6 in case of the classic or original transformers. So after that the final decoder output is given to what? Linear layer plus softmax to generate probabilities of the tokens in the output. Okay. So when you look into the summary, please understand this summary. Okay. So we have three blocks. What are those three blocks? Masked multi-head self-attention, masked multi-head cross-attention, feed forward. Okay. So masked multi-head self-attention will allow decoder to attend only previous tokens, which prevents knowing the next values in the target sequence. Multi-head cross-attention will allow the decoder to attend to the relevant source tokens, and then feed forward will introduce non-linearity and help us with what? Transformation. Okay. So this is all about what? The decoder block. Okay. So what is the difference between decoder and encoder? In decoder we have what? Two. In encoder we have, how many attention mechanisms are we applying in encoder? Only one. What is that attention mechanism? Self. How many attention mechanisms inside the decoder? Two. What are they? Self and cross. Where are we applying self-attention? Masked help. What do you mean by self-attention? All Q query values generated together. What is cross-attention? Query from one block, keys and values from other block. Query from which block? Decoder masked multi-attention block. Keys and values from where? Keys and values are from encoder output block. What is X? Input of encoder. What is Z? Output of encoder, which is contextualized word embeddings which are generated as features. What is Z? Output of the encoder. What is Y? Input to the decoder, which is nothing but the target sequence. So if you understand this, you would understand the code. What is D model? The vector, the n-dimensional vector space that I am taking for each token. What is number of heads? How many times I want to process my multi-head operation. Okay. Now when I talk about this entire transformer model, how do I process that? Now we have designed encoder block, we have designed decoder block. Now I want to put it all together. So how do I do that? Training the model. So how do I train the model? First I call encoder, take the output of that, decoder, and then linearity and then softmax. 4 layers in the training loop. Encoder, decoder, linearity, softmax. Are you all clear with this? Okay. So we'll have quiz. Okay, you take break after that quiz and then we'll get into the coding part. So today we'll see the entire coding of what? Transformer, which includes what? Encoder part, decoder part, and all put together. Okay, it takes time. So hence just go quickly, come after 10 minutes. So what are we going to do today? Neural machine, what? Translator. Okay, NMT. Using what? Neural machine translator using transformer architecture. Okay. Now, first let's understand, before we actually go into the code, first let's understand the sequence and all the steps that we have recapped. Input sentence, target, source sentence, target sentence, and see how are they processed. After that we go into the code. Okay. Now what do you see there? I have 2 sentences. What are they? What are they? I love AI, which is the input sentence, which is in which language? English. Which is my input, which is X. Which is what? X. What is the target sequence? Hindi. So what translation I am doing here? English to Hindi. So when I say I love AI, what is the translated output of that? Mujhe AI pasand hai. Okay. Now listen to me. You may get more or less the same kind of transformer in the exam, but I'll tell you the change, difference. Okay. So here how many sentences I am taking for? Here I am doing what? English to Hindi translation on one word. Upper word embeddings, generation, positions and all that would be different. In your exam, we might give you what? Multiple sentences or a data set also. Because if I train on this, the output may not be accurate because machine understands is trained only on these 3 words. What are they? I love AI. But if I say, tell me what are you doing? It will not understand because the transformer model is not trained on tell me what are you doing. So if you give more words in the corpus, the machine or the transformer model will learn more words and their corresponding translations and will give you the proper output. Okay. So there are 2 things that you have to understand here. First thing is how a model works. That is our main agenda. Take one word, one sentence in processing and see how model is working. But in fact, after this, what would be your next step? Once you know how the model works, you have to predict good results also. So how will you generate good results? By training the model with what? Large data set. So we are training you on how a model works, but we will test you on what? Generate the proper output, for which you have to train what? The model more with more sentences. That you have to work and come. Okay, that I will tell at the end of the class. Okay. That would be the difference. Same translation only. We are openly telling you same translation transformer only we will give you. Maybe translation or next word prediction. But whatever it is, it will be what? Transformer only for the exam with what? Some twist. Twist and n dimensional, d dimensional, we will tell you, there you have to change. Number of attention heads we will tell you, there you have to change. Number of encoder layers we will tell you, there you have to change. You have to read what? Read what we are giving about the question and then answer the block. లేకపోతే టెస్ట్ కేస్ పాస్ అవ్వదు, మార్క్స్ 0 వస్తాయి. దట్ ఈస్ ఫర్ షూర్. Is that clear, everybody? So these are going to do in the exam, which is coming, which will be there the next week. Okay? Yeah. So let's get back to the code. So what is the sentence I have taken? I love AI, which is what? The input sentence or source sentence. What is the target sentence? मुझे AI पसंद है. So I am going to train my transformer with both, where I give my source sentence to the encoder block, I give my target sentence as input to the decoder block. This is what we have seen. Okay. So first I do what? I generate some positions for what? All the tokens. So when I say tokens, I have to generate the positions for both source sentence and target sentence. Why? Because for the encoder, source sentence would be processed. For the decoder, target sentence would be processed. Here also I have to generate input embeddings and word embeddings. Position encodings, here also I have to generate word embeddings and position encodings. That is the reason. What am I doing after I take the sentence? I am doing the tokenization or word positions for what? All the tokens in the given input, source and target. Okay? Look at this. Next, what do? I generate the word embeddings. So what is the d-dimension vector that I have taken here? 4. Why am I calling it as 4? Because each word, I love AI, each word I is represented in 4 dimensions, 4-dimensional vector. D-dimension or D model is equal to what? 4 here. Madam, ఏంటి నిన్న 8 అన్నారు, ఈరోజు 4 అన్నారు. That you have to change in the code. For that reason, I am wantedly changing this. Is that clear, everybody? What will happen if I take more number of contexts? More training. That is, you are giving more possibility for the model to understand or depict the meaning of each word. Okay? To understand the context again. Next, what do? Calculating what? Positional encodings by using what? Sine and cos. That we already know. For I love AI, I find the position encodings. After that, what do? I add word embeddings and position encodings. Do you see that at the bottom? I is equal to the word embeddings added with what? The position embedding. So I generate the final vector. Okay. Now what do I do next? I have taken my input sequence for the encoder, which is the source sequence, which is in English language. I have generated word embeddings. I have generated position encodings. I have concatenated them. And then the output of this word and position encoding, I am giving it to what? The encoder block. Where inside the encoder block, what do I have? Inside the encoder block, I have what? Multi-head attention. So what do I do in multi-head attention? First, I generate random weights for QKV. What are those random weights? WQ, WK, WK, which are multiplied with what? X. What is this X? Input sequence. Now when I multiply X into WQ, X into WK, X into WV, what do I generate? Q matrix, K matrix and K matrix. After that, what do? I generated QKV and then I'll try to compute the attention scores. How am I computing the attention scores? Q into K transpose by square root of DK. Apply that to what? Softmax function. And then computed the weighted sum by multiplying the normalized attention scores with what? The values. This is what we do in the multi-head attention. After that, this is multi-head attention, single head done. But no, we are not just stopping it there. We have to do that for n number of heads. Okay, that is called as what? Linear projection. That is applying MHA in step 3. What did I do in step 3? self-attention. Step 3 is what? Self-attention in brackets encoder, because we are using self-attention in decoder also. So you have to be very specific here. Okay. So I am performing self-attention in encoder, and then using linear projections, I am applying multi-heads inside what? The self-attention mechanism. Are you clear? Yes or no? Now look at that QI, KI, VI. What are those QI, KI, VI? Output of multi-heads, which are obtained by what? X final. What is this X final? One self-attention output that I got into what? The weights that I am generating for individual attention blocks. Okay. Now again do the same thing, applying softmax on that and all that stuff. Okay. So finally, what is the MHA output? Concatenation of what? Those multiple attentions that I am taking. So can you see MHA is equal to what? Concatenation of attention 1, attention 2, attention 3 and so on. And then finally, what is the final output of MHA after linear transformation? After forward, feed forward, contextualized word embeddings. Okay. So after that we give it to what? After MHA we give it to what? Feed forward, where I have two layers, two fully connected layers. First layer, I take W1 attention output plus B1. I apply ReLU on FFN1, and then FFN2 is what? The second layer, which is W2 into FF1 plus B. Yes? Are you clear with this? After this we go for what? The decoder block. In decoder block, what is the first step? Masked multi-head attention. So what am I doing in masked multi-head attention? I am again generating, first I go for masked multi-head attention, where I generate what? QKV. But here QKV is for what? Target sequence. Okay, can you see that? For example, if you are predicting the first token Mujhe, why I am taking Mujhe here? Because this is decoder. I love AI, where I is the first word that I am depicting, which is what? Mujhe. Okay. So that I am giving it to what? Masked multi-head attention as the input. Okay. So what do we do again in masked multi-head attention? Same thing. What is that same thing? Q into K transpose by square root of dk into V. But before that, what is the formula here? For attention in encoder, the formula is softmax of Q into K transpose by square root of dk into V. But here in the decoder, how do I write it? I rewrite it as softmax of Q into K transpose by square root of dk plus what? Masking. That is, I am just giving the question. I am hiding the answer and I am asking the model to predict the answer for that. Okay. Into V. Did you all understand the difference between attention mechanism, self-attention in the encoder and self-attention in the decoder? Masked. Okay. Now what do I do next? Encoder decoder attention, which is multi-head attention. Why am I calling this as encoder decoder attention? Because keys and values are from encoder output, query is from decoder masked multi-head attention. Hence, this is all. This MHA block inside the decoder is also called as what? Encoder decoder attention block, or we also call it as what? The cross attention mechanism. Are you all clear with this? Now look at that. What is cross attention mechanism here? Softmax of what? Q of decoder into K transpose of what? Encoder divided by square root of dk into V of what again? Encoder. Because Q is from the decoder, K and V are from encoder. This you will understand the coding part. That is the reason I want to put them as words in the steps and then we'll go for the coding. Are you all clear with this? Two changes. This change in the masked multi-head attention. This change in the multi-head attention of the decoder block. Okay. And then is there any change here? FFW would be same. Okay. What is FF1? FFN1 is ReLU of what? W1 into decoder output plus B1 There it was encoder output. Here it would be decoder output. What is FFN2? W2 into FFN1 plus B2. After that, we'll have the words generated. For I love AI, first mujhe will be generated. After that, AI pasand hai. Are you all clear? Okay. Now let's get back to the code. So what was step 1? Installing the torch.txt. Okay. After that, what do we do? After that, what do we do? Yes? Import what? Import what? Import the libraries. What are the libraries that I am importing? Torch.nn. What is this torch.nn? The neural network model which performs all the operations. When I say all the operations, I am just doing feed forward. I am not calculating loss, I am not calculating gradients backward. Everything would be done by what? The NN module. When we tried to develop ANN from scratch, where we didn't use NN, we did what? Forward propagation, loss calculation, backward. But we are not developing transformer from scratch. We are using which block? NN module, which will take care of the entire processing. Okay. Now look at the code here. Okay. So first I am importing what? I am importing what? NN, which will actually perform what? All the internal operations of a neural network module. Okay. And then I am also importing what? From NN.functional I am importing what? F. So this F is actually used for using what? All the activation functions. That is, so what are the activation functions that we are using in the code? Softmax and ReLU. Where are we using softmax and where are we using ReLU? Yes? Softmax inside the self-attention block, ReLU inside the feed forward. Okay? Now, this is step 1. Please understand, I already explained. Once again, I want to repeat because this is the most important concept that we are going to end today. Okay? Now, what am I doing first? What am I doing first? I am importing the modules. After that, what do I do? Vocabulary creation. Vocabulary creation with word positions. What do you mean by vocabulary creation with word positions? I am trying to read what? I am trying to read the input and output sentences. So what is the input sentence here? I love AI. What is the target sentence here? In French language. Madam, akkada Hindi annaru, ikkada French annaru. Rep German adugutam, Telugu kuda adugutam. Okay? Is that clear? So we'll give you Telugu or we'll give you Hindi because everyone knows Hindi. Okay? Is that clear, everybody? Okay. What am I doing next after giving the input and target sequences? I am going for what? Word mapping. What is this word mapping? Vocabulary creation of each word token that I am generating. After that, what do? I try to tokenize the sentences. So which sentences do I tokenize? Both. Because I use input sentence tokens for the encoder block. I use output sentence tokenized for the decoder block. So I have to tokenize what? Both input sentence and target sentence. Okay? And I am tokenizing them and converting them into what? Tensors. Why am I converting them into tensors? Because when you use NN, PyTorch NN module, you have to represent every word vector or every embedding vector into what? The tensor. Okay? So there are 4 steps here. What are those 4 steps? First is what? This is first step. What is that? Training data. I call this as what? Training data. In training data, I give both input language and output language. What am I doing next? Generating the tokens. Am I generating the tokens or I am generating the word positions? word positions for all the tokens. What am I doing in the third step? Generating the tokens for the given input sentence. What am I doing last? Converting the input target sentence into tokens, output target sequence also into tokens. Okay. Now read this. What does sentence EN sentence FR represents? English and French sentences which we are wishing to translate. What is that word map EN, word map FR? The dictionary mapping words to integers. That is the vocabulary that I am creating. What is that? Why are we using padding? Why am I using padding? Because when I say I love AI, I have 3 tokens. When I am converting that, mujhe AI pasand hai. How many tokens? 4. So in order to avoid this discrepancy, I pad them with zeros. Extra words that I am generating in the input, the output would be padded with zeros or vice versa. Okay. Next, I am creating a function which takes a sentence and a word map dictionary and try to split the sentence into individual words. So the output of these words are given as what? Tensors. This is step 1. So what do I do in step 1? Given the training data, find the word vocabulary of the training data, divide the training data into what? Sentence tokens, and then generate the tensors of input and output target sequence or input sentence that I am taking. Okay. Now what is step 2 now that I have to do? Positional encoding. Okay. Now tell me, what is the need for positional encoding? What is the need for positional encoding? Because unlike RNNs, you're passing all the sequences at a time. So the position of the word will be what? Changed if you don't give position number. Yes or no? Here when I talk about transformer, I am processing all the words at a time. So when I am processing all words at a time, the sequence matters. If I say I ate an apple, you will get a proper sentence. But if I say apple I ate or ate apple I, the translation would be what? Wrong if you don't give the position encoding. So that is the reason we go for what? The second step, which is what? Positional encodings. So please read this. Since transformer do not have inherent understanding of word orders, we consider what? Positional encodings. Okay. Now try to understand this code. Okay. Now here, look at each word. Okay, each parameter. See that D underscore model? Can you see this D underscore model? What is the D underscore model? Dimension of the token embeddings. Please make a note of that. What is D underscore model? The dimensions of the token embeddings. What is that max length? The sequence length that I am taking, because sometimes I may give you 10 words in a sequence, sometimes I may give you 20 words. So I am just giving the maximum length declaration is what? 5000. Okay. Now, what am I doing here? What am I doing here? Can anybody tell me? First, I am defining a class called position encoding. Okay, I am inheriting the properties using the super module. Okay, and then look at this. Self.encoding is equal to torch.zeros of max length comma D model. What do you mean by this? What do you mean by this line? What does that tensor 0 torch.zeros do? It will create what? It will create what? What does that torch.zeros do? Self.encoding means what? I am taking a basic tensor. I am creating the tensor, an empty tensor 0 initially because I still didn't start my processing. Please understand this. Okay. Now what are the parameters I am passing inside that tensor? Look at that. Max length comma d underscore model. What do you mean by max length comma d underscore model? Max length is number of words that I have in the sequence. How many words did I take? I love AI. So what is the max length in our sentence? 3. What is the D model? What is the D model? Hooray. What is the D model? Vector dimension for each word. That is, I am telling, I want you to create a matrix of what? 3 words, which is max length, I love AI, where I is what? D dimension. The D dimension I still not declared. The word vector size that I am taking. So I am just creating a simple tensor in which I am passing the parameters of what? The sequence length and the D dimensional vector. Okay. Now after that, what is the sentence that I am taking? Position is equal to torch dot arrange. That is, I have even position and odd position. Yes or no? I want to create even positions of the word tokens and odd positions. So when I talk about I love AI, how many evens and how many odds are there? 1 odd position, which is 2. Am I correct? 1 even position, which is 2. 2 odd positions, which are 1 and 3. That is what I want to generate. So I am using torch.arrange for what? Look at that. I am using torch.arrange to start the sequence with 0 till what? The maximum length, which is what? 4 or 3, whatever that we take in the sequence. D type torch.float unsqueeze. Why am I using this unsqueeze? Because I am creating a tensor where I want to add a extra dimension. Okay. Now, please note it down. Please note it down. Torch.arrange will create a tensor of position ranging from 0 to maximum length. Torch.arrange will create a tensor ranging values from 0 to maximum length. Okay. Now look at the next one. Now I have created that range. Now I have to divide that range into what? Even and odd. For even we use which way? Sine or cos? Sine. For odd we use what? Cos. I am doing the same thing here. Self dot encoding, divide that with sine and then cos. Okay. Again I am applying unsqueeze to get back to the original dimensions. Okay. So this is how I do what? This is how I do what? Positional encodings. What is the defined forward of self comma x? What is the defined forward of self comma x? What is the defined forward of self comma x? Read that last point. The forward method adds the positional encoding to the word embeddings to ensure that the model is aware of what? The position and the word embedding. Are you all clear with this? I have generated word embeddings, I have generated positional encodings, and I have to add them with respect to which function here? Define forward method here. Clear? Now look at that. Adds batch dimension, and then I am adding positional encoding to the input embeddings using that forward block. Okay. Now I am trying to print the position encoding values and before and after. Don't forget about this. What is the next block? What is the next block? Multi-head attention. Okay. Now look at that. Look at this here, please. What are we doing in multi-head attention? Multi-head attention is a key component, I say, in the transformer. Yes or no? Do you all agree with me? Okay. So what am I doing here? What is that D model and number of heads here? D model is what? The dimension of the model. Number of heads is what? the number of repetitions that I want to take here. That I will declare at the end, that we will see it later. Okay. Now look at the code here. I say self dot num underscore heads is equal to num underscore heads. I write self dot d model is equal to d model. Self dot d underscore k, self dot d underscore v. Am I writing q here? Why? Because I want the output of multi-head attention only as what? K and V. Because this is what I am going to give it as input to the decoder. Are you all with me? Yes or no? Okay. And then I write what? Self dot query, self dot key, self dot value. I am applying nn dot linear. Applying the linear transformation to this. Okay. So these are the linear transformations to project what? Observe this, self.query, self.key, self.value. So these are the linear transformations, that is I am applying to the fully connected layer to project the input tensor into three different values which are query, key and values. Okay. So I am printing them separately as you can see. Self.query, nn.linear, self.key, nn.linear, self.value, nn.linear, self.fc. What is that fc? Fully connected layer. Okay, so I am generating query matrix, key matrix, value matrix. Are you all clear? Now look at this. What is this forward? What is this forward? The previous one is only one multi-head attention. Now here I am trying to generate what? One single head attention and concatenate all them together. Okay, so what do I do in single head attention? Q into K transpose, divide that by what? Square root of dk, add softmax and then multiply that with what? V. Are you all clear? Yes or no? Okay. On that above, what is this QKV? I am updating them. What is that QKV? I am updating them. That is Q, write down here. The QKV here represents the learned linear transformations. The learned linear transformations to the input X. The learned linear transformations to the input X. Okay, now look at that. How am I calculating attention scores? What is attention scores? Q into K transpose. Look at that. I am matrix multiplying Q with what? K transpose. After that, I am not doing any masking because this is encoder block, right? After I do that, I calculate attention weights. How do I calculate attention weights? Applying softmax. F dot softmax. What is this F? The function that I have imported from the neural network module. So, F dot softmax of what? Q into K transpose. Are you getting or not? What is the formula? Softmax of Q into K transpose divided by square root of dk. So, where am I doing Q into K transpose divided by square root of dk? In that variable called attention scores. Can you see that? Torch dot matrix multiplication of Q comma trace transpose divided by torch dot square root of what? D model. Okay. Now this I am applying it to attention scores where I am generating the attention weights. So what are attention weights? Softmax applied to what? Attention scores. Now after that what do I do? Multiply that with V, which I am calling it as what? Attention output. Now look at that. Attention output. Attention output is equal to what? Matrix multiplication of attention weights. What is attention weights here? Softmax of QK transpose divided by square root of dk. That I am multiplying with what? V. Are you all clear? Yes or no? Okay. I am just doing that. Attention scores, attention weights, and then I am applying that to what? Attention output. I am printing that. Attention output before final layer, attention output after fully connected layer. Okay. Now after MHA, what do we do? Feed forward. So what are we doing in feed forward? One linear layer, apply ReLU, another linear layer. Okay. Look at that. What is that self.fc1? The first linear layer. Self.fc2, the second linear layer. I again define a function where I say fc2 is what? ReLU of fc1 into w2 plus b2. Is that clear, everybody? Yes or no? So what is w2 plus b2? Which is obtained as the next weight for the second layer. So this is what? The feed forward network. Okay, I am trying to print input to the feed forward, output after first linear, output after ReLU, output after second linear layer also. Okay, next, what do I do in encoder? What do I do in encoder? Multi-head, normalization, feed forward, normalization. Can you see that define forward? In the define forward, what am I doing first? Attention output, which is the output of multi-head attention. I am doing that. Second, I am applying normalization. Third, I am applying what? Self dot feed forward. And again, I am doing what? Add and normalization. I am returning what? X. So the output of this is what? Z that I am calling. This is what we have done in the last class, right? Now let's get back to decoder. Please understand decoder. Same like encoder, but two changes. What are those two changes? In MHA, masked MHA, I am doing masking. Where am I doing masking? Q into K transpose. After that I apply what? Masking. Okay. Now let's look into this. Please look at this. First, multi-head attention 1. Self dot multi-head attention 1 is what? Masked multi-head attention. Self dot multi-head attention 2 is what? The cross attention or the encoder decoder attention. Okay. Are you all with me? Okay. How many normalizations I am doing here? 3. Norm 1, norm 2, norm 3. So total I have 6 blocks here. Self dot multi-head attention 1, which is masked multi-head attention. Self dot multi-head attention 2, which is encoder decoder cross attention. And then I have feed forward. After every layer I am doing what? Normalization. The first block is not in sequence, just class encoding representation. The second one in the forward, I am putting that in order. What is the order? First I take what? Attention output 1. What is that attention output 1? From masked multi-head attention. After that I do what? Normalization. After that I do what? Self dot multi-head attention 2. What is that self dot multi-head attention 2? The cross. Now observe that. Inside self dot multi-head attention 1, what am I passing? X comma target masking. In multi-head attention 2, what am I passing? X comma source mask. Are you getting my point? What is multi-head attention 1? Masked multi-head attention. In which I am passing what parameters? X comma target mask. Okay. What is multi-head attention 2? Encoder decoder attention or cross attention, where I am passing what? The source, that is the output of the encoder. Are you all clear? After this I am doing what? Normalization. After that I am giving it to what? Feed forward. And then I am again doing what? Normalization. What is the change in the decoder when you compare it to encoder? One more block added. What is that one more block? Masked multi-head attention, which I am representing it as what? Multi-head attention 1. Are you all clear with this? Now the last step. What is the last step? the transformer model, put it all together. So in this, I use what? I use the encoder block, I use the decoder block, I use the linear, I use the softmax. Okay. Now let's look into this. I'll just zoom this. Okay. Now look at this. First I am doing what? Self dot embedding inside the transformer. Now forget about decoder, forget about encoder. Let's get back to the whole transformer model. First step is what? Embedding. Embedding of what? Embedding of vocabulary size and what? D model. And next I do what? Position encoding. First I do the word embeddings. Next I do what? Positional encodings. Next I go for what? Encoder layer. Now correlate this with architecture. First I take the input. I do the embeddings. I find the positions. Now give this to what? Encoding layers. I give this to what? Encoding layers. After encoding layers, decoding layers. After decoding layers, after I decode the layers, what do I give? Give it to linear and then softmax. Are you all clear with the transformer model? What is step 1? Self dot embedding. After that, self dot position encoder. After that, self dot encoder layers. After that, self dot decoder layers. After that, finally, NN dot linear. I don't write self dot linear here. NN dot linear. Are you all clear with this? Self dot FC output is nothing but NN dot linear. Did you all understand? Yes or no? Now look at the next one. Okay? Now please understand this. I am putting it all together now in the forward. Okay? First I take what? Source sentence. Next I take what? Target sentence. Now look at that. Source sentence is given to what? Encoder. Target is also given to what? Is it encoder or decoder? Why did I put encoder here then? Look at this. I am passing this encoder to what? Self-embedding of the target. That is the decoder block. Okay, just for nomenclature, I have just put it like that. Okay, now look at that. What is the encoder output? Encoder output is what? The source sequence. The encoder output is what? The source sequence. What is the decoder output? The target sequence. Okay. So first encoder, decoder, and then the final output, which is nothing but self.fc.out. And then finally I'll return the output. Okay. So as you can see, let's read this. Read this. The transformer model is the overall model that uses what? Multiple encoder and multiple decoder blocks. So embedding layer will convert word indices to word vectors. POS encoder will add position vectors to each of them. Encoder layers and decoder layers nothing but stack of them in the encoder block and decoder block, and then finally I'll have my final output, which is the linear conversion of it. Okay, so this is the transformer model and this is the prediction module. So what am I doing in the prediction module? I'm just printing them. What am I printing? Can you please read that? I want to print the input tensor. I want to print the target mask. That is, I want to generate a mask for the target sequence, initialize the target sequence, predict the output target, apply the softmax, and then generate the output. Is that clear, everybody? So this is all about how the transformers are built and developed. Is that clear? So 7 steps. Step 1 is what? Step 1 is importing the libraries, give the training data, embeddings and tokenization. Step 2, word embeddings or positional encodings added together. What added together? Word embeddings and positional. Step 3 is what? Singlet attention. Step 4, with singlet attention multiple times. Step 5, feed forward. Step 6, encoder layer. So for encoder we have till step 6. Step 7, The decoder layer in which we do what? Masked multi-head attention, and then feed forward and all of that put together. And then finally the whole transformer model where we use what? Encoder block, embedding, positional encoding, encoding layers, decoding layers, and then linear. 5 steps. Is that clear, everybody? So this is how we design what? Transformers. Look at this now, the last step, which is important. Initializing the models, model parameters. Okay. Now here, what is the vocabulary size in English? I am just giving length of that because I don't see if it is 3 words, I can say it is 3. But if I give you some random 20 or 30 words, you won't sit and count. We use which function? Length. Okay. What is the D model I have taken here? One word represented in how many dimensions? 128. Number of heads is what? 8. Number of iterations is what? 8. Number of encoder layers? For sample I have taken 2. Tomorrow we may give number of encoder layers as 6 or 10 or whatever it is. Is that clear? So we will give you D model length, we will give you number of heads, we will give you what? Encoder layers, decoder. Depending on that you have to do, otherwise your test case will not pass. Is that clear, everybody? This is how we initialize the model. We'll put this as read only. Remaining things you have to do it. Are you all clear? Okay. So this is all about your transformer models. Okay. So any doubts in the transformer model?